Welcome to Brain Vision.
Okay, this is another one of those alien planet type of problems. So we do two experiments, one horizontal and one vertical. So the horizontal experiment, we apply a force of 12 newtons. Your ball or package or whatever goes 16 meters horizontally over a time interval of 2 seconds. So the question, and then it starts at rest. So it has an initial velocity of 0. So the question is, the ultimate goal is what is the weight of this object on both Newtonia and Earth, but we will need to know what the mass is. So that's what the purpose of this experiment is. So let's use this kinematics equation in order to find the acceleration, and then later on we'll find Newton's second law in order to find the mass of this object. That will be very, very helpful. We just said that the initial velocity is 0, so that term goes to 0. Do a little bit of rearranging in order to solve for accelerations. That's 2 delta x over delta t squared. And then we plug in numbers. That's 16.0, and then down here 2.00 squared. So get an acceleration of 8.00 meters per square second. Good. So now we apply Newton's second law in order to find the mass. So that'll come out to be force divided by acceleration. So that's 12.0 divided by 8.00. And then we get a mass of 1.50 kilograms. So let's not put a box around that, but let's underline it because that's an important number for later on. So that was experiment number 1. Let's do experiment number 2. We know that the ball begins at rest. We drop it from a height of 10 meters, and then it hits the ground after a time interval of 2.58 seconds. That's kind of a very precise number, but we'll see why they chose that number in a second. So we get use the same kinematics equation, but this time in the vertical direction. So we have gravity being the source of acceleration. And again, this is on that foreign planet. And like before, we know the initial velocity starts at 0, so that makes our lives easier. That first term goes to 0. Do very similar algebra to be able to solve for that gravitational acceleration. Plug in numbers, 10 up here, 2.58 squared. And sorry, this is a displacement of -10, so that gravity will be directed downward, and then we get negative exactly 3.00 meters per square second. So that's why I think they chose that very, very exact time interval. So now we can solve for the weight on Newtonia finally. And we do that by multiplying the mass that we already found by the gravitational acceleration on Newtonia. Sorry for the off notation, but that's the same number that we just solved for, and that's the absolute value, and that's the 3. So the weight on Newtonia is 4.50 newtons. And then we do the same exercise, but this time for Earth. Mass is the same wherever you are, but gravitational acceleration differs. So same mass that we found before, but this time we use our gravitational acceleration of 9.81. And then the weight comes out to be 14.7 newtons, 2 3 significant figures.